Well, actually, we are achieving, we are celebrating here the achievement of a big team. And I just represent them in some way, but they should not be mapped to me only. That's not okay. But yeah, let's say that very clearly. Okay, so 7 years of Math4UQ at RWTH Aachen, right? So let's go to it. I already acknowledged, unfortunately, we have this Zoom thing in between. I never know how to get rid of it, but okay. I think you can survive with this. So why did we have this Math4UQ chair at RWTH? Well, it was founded in 2018 and with a very generous funding from the AVH. It was extended by 2 years, essentially after 5 years of successful execution. As a mission, we had to advance mathematical foundations and numerical methods for UQ, while still bridging mathematics, engineering, and data science at RWTH. You know that RWTH is one of the key nodes in engineering at Germany, so this was very important, actually. And we grew despite many challenges, right? I mean, space at the beginning, COVID that hit us 2 years through the execution and other things. But let's see. No, sorry.
You just select the slide again.
Yes. Okay, so this workshop, as I told you, is a culmination of my AVH professorship. We would like to walk you through some research achievements, teaching, and collaborations. And of course, it's impossible to cover all, right? So I had to actually make some highlights on things and shorten many things. So I apologize in advance for those that actually have done a fantastic job, and I cannot actually put them here inside. Now, we celebrate diversity and we harness diversity in our research, right? 21% approximately of our team is made of females, and we have a wide set of nationalities in our team. This allows you to bring talent from all over the world, right? And achieve many things. We work in different topics, right? I list them here. We don't need to read them up. Most of you already know and have worked in some of them with me. And not only we work in developing fundamentals for mathematics in UQ, but we also look at applications, right? I'm an engineer by training, so we try to have this as a motivation. Here, for example, we list, again, this is a limited list, and we have more, right, in practice. Some examples relate to aerospace, and this is me with Philip at the entrance of DLR Bond, right? Where's Philip actually here? Yeah, there's Philip. Okay, yeah, and that visit actually kicked the establishment of the DLR professorship W2 at RWTH, that hopefully is coming in the next few months or so. So some examples of applications, like I said, aerospace and medical systems, right? And renewable energy management, wireless communication, computational finance, and I could keep going, right? What about the shared achievements at a glance? Well, here I put just fun, a little bit of a map of where our people come from. And again, this is not a complete map. I was not able to actually have the time to put up to date the graph, right? But at least some fun dots you can start guessing. As an output, more or less, we have like 10 publications per year, 500 citations in Scopus per year. And we have placed alumni not just in the academia, but also in the German industry, like Telecom, Allianz, and other places as well. While other people chose to not go to industry, right, and transition from master to PhDs and PhDs to postdocs, not just in our chair, but other chairs as well in the math department and elsewhere. We kept our vast fingers of collaboration as we did, and I want to announce two very good things. One already I mentioned to you, right? This year funded the W2 professorship that is coming up and was obtained through the chair. And the other thing, Adon just made my introduction, right? So I make an introduction for him too. So former PhD from KAUST, professor in Heriot-Watt, has been awarded recently the Humboldt Research Fellowship for Experienced Researchers and started already at our chair in July 2025. And we look forward to fantastic things out of as usual, right? Now, what about training and development of talent? We have produced essentially a few PhDs at the chair. You can see that this is again a wide variety of topics, right? Ranging from stochastic optimal control for important sampling to optimal experimental design, right? And we still have 3 more to go in the next year and a half or so. While the PhDs were developing, our postdocs and W1s actually found better positions elsewhere and transitioning to those, right? So this is again a testament to the ability to recruit talent, but also to develop it at the chair. And yeah, I'm very proud to have six of those placements. It's fantastic. And now we have friends that are powerful everywhere. So then I can retire and they will help me to survive through retirement. Another mark of class and excellence is the production of habilitations in the German system, and we had 2 in these 5 years or so, 7 years or so. One by Luis Espat, who is sitting in the back, right? And he managed actually to publish in Springer the content of his habilitation, which is also recognition. And Alexander Litvinenko, who Alex is over there, excellent, produced and defended finally his habilitation this year in 2025 on low-rank tensors methods in uncertainty quantification, right? So very proud of both of you. Okay, and going through the cycle, right, as usual. Master thesis were also a pivotal part of our pipeline, right? And we had approximately 15 master theses successfully defending, again, over a wide range of topics, right? Containing also Makin-Blasov approximation, a little bit of computational machine learning, coding projection, and so forth. So this was really fun. And many of them then transitioned to higher things in similar topics or so. All in all, I think it's like 2 habilitations, around 7 PhDs, 15 master theses, and bachelor theses on the order of 25 or so. So you can see the pyramid more or less developing from those numbers. How do we do in the master teaching contributions? Well, normally we developed and ran 3 courses at the master level and 6 seminars per year. On top of that, there has been, and is still going, a weekly hybrid seminar on stochastic numerics with international speakers. COVID forced us to actually adopt this hybrid format, right? But even though we were not so fond of it before, we ended up appreciating it very much because it was very easy to convince people, okay, give me a talk online, right? Rather than come here, blah, 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 blah. So even though we still have the freedom to invite those that actually can come, right? For those that actually are difficult to get, this is a better option, and we can have access to people that otherwise we wouldn't. We improved, I mean, through COVID, we changed the way we teach, right? Adapting more to remote and hybrid formats. From the beginning, we were very much project-based, oriented in the learning. And of course, we always try to match the teaching at this level with the research. Okay, so these are some ads from those courses. And then there was the big, big load from the service teaching, right? So I really didn't expect it to be this burdensome when I came here. Of course, I was completely an outsider in the German system. But I think, again, we managed to not only satisfy the load in these high mathematics courses that essentially are 3, high mathematics 1, 2, and 3 for machine and bio, right? In engineering here, this is mechanical engineering, the core engineering part of RWTH, running more or less 10 HIBIs and 4 postdocs for each course delivery. And so far, we have accumulated like 6,000 students that went through this higher mathematics. We changed the way these courses are taught, right? I mean, inspired again by the COVID and thinking that actually there were like sometimes 800 people in the room, right? We changed this to a more interactive through technology, right? Flipped class and actually not only just somebody delivering the class, but somebody watching the electronic room, right? To be able to deliver up to 100 questions per session, when in fact before the interaction level was way lower, right? So this has produced not just this level of interaction at the course delivery, but also better evaluations from the students, much better, and better results at the exams as well. So this is all documented and has created an impact on the way these courses are taught. Of course, in the process, there was a creation of a huge amount of electronic reference material in videos and so forth for the students. Okay. Timeline for key milestones. We started in 2018, essentially with empty space, no internet, no secretary, and we had to build from there. We built our place maybe in Kakastrasse, what is called, almost 3 kilometers away from the main math building. It was an interesting experience to develop our place there. And when we were more or less finishing establishing ourselves there, COVID hit, and then we also had to move again to the offices that we have right now. They were not ready, so we had to work a lot to establish ourselves, and we did against all odds, right? So in the process, again, like I said, the 2 W1s left for higher positions, right? So I kept going until now for the delivery. Okay, so before I think we transition from here, which is essentially the timeline of the evolution of the chair, to some very short highlights on the research side. How am I doing with time?
Very well.
Very well. Okay, I'm surprised too, actually. If you have any questions, by the way, you can stop me. All right, so I think most of it I already mentioned. So the important thing is that in COVID also we had to switch to hybrid teaching, right? So this entailed a lot of creation of material that was recorded and curated through the years. So that was not a minor thing either.
So who's the longest serving besides yourself in the group? Who was the longest in the group? The person who was employed the longest?
Well, Alex has been with me since ever, essentially, right? So I think immediately Eric also has been, but he's not here, right? So he's in KAUST, right? So if I have to pick somebody in KAUST, I think here, I think it would be Alex, right? Am I wrong? I mean, somebody can just contradict me, but I mean, from the top of my head, this would be Alex.
Shima, I assume.
Shima, of course, Shima has been from here, right? Essentially, she would correct me. She would say, Raúl, I was hired end of December. And I said, well, this is a poetical license, right? I mean, because I mean, if you say she was hired in 18, you miss the point that actually I had to run the first months without a secretary, right? So I put this on purpose to make it clear that I had to run. And I didn't know German at all. So that was a very interesting situation. I look back and I don't understand how I was able to manage, actually. Okay, any other question? No? Okay, so just about the research, right? I mean, again, I apologize. I cannot cover everything. I have to make some quick highlights of things. So, for example, I cannot talk about what we did in inverse problems, right? I cannot talk on hierarchical approximation, for instance, what we did on the development of numerical smoothing techniques, in particular, those that are used for the efficient evaluation of densities of processes, right? For example, with Shiheb and so forth. So I apologize. Some of the things appear in the poster session that will be today, right? Well, I encourage you that actually take my little piece here as a motivation to engage with people at the poster, and of course with me if you have more questions again, but time is limited. So first snapshot is connected to the work with Luis and with Carlon. Carlon is over here, right? It's also helping very much with the organization. It relates to stochastic optimization, which is connected to applications, stochastic control, finance, machine learning, and so forth. So most of you are already familiar with stochastic gradient descent, Adam, and other very powerful methods that are used to do stochastic optimization. So there are two challenges mainly, among others, in this area. One is that you don't have access to the exact gradient, so we only have samples of stochastic gradients, and this introduces a large gradient noise that deteriorates the convergence, or learning, if you wish, if you come from machine learning. And there's also cases that are of interest that contain large condition numbers. And we said to deal with these two things, the first way was to actually introduce a control variate that uses information along the paths, which is called the MICE estimator, multi-iteration for MI, right? It's a variance reduction gradient estimator based on a hierarchy of iterations. So it's not like the usual multi-level, right? Things are not independent and they're accumulated through the history. The way we do it adaptively, we construct a hierarchy of iterations, and we have to keep this hierarchy tight to be able to maximize the efficiency of the method. But this is done again along the way. We have results on the convergence, right? And we provide as well stopping criteria to terminate and then guarantee a certain accuracy, right? So this method, this estimator is very flexible, right, and can be coupled by any stochastic first order, including Adam, right, and others as well. So it's not that you have to go with this and then drop Adam or things like that. No, it's not like that. Now there's still some issue left, right? Even though you compare with other methods. I mean, here working with logistic regression, these are examples with large data sets. Which are like test beds for comparing methods, right? So you see here comparisons in terms of iterations, and here comparisons in terms of cost, and cost being here the number of gradient samples that we have to produce to advance the method, right? So in all this we came up well. The method actually has theory that backs it up only in the strong convex problems, and that's why we are showing here logistic regressions. The results for non-convex actually are a bit mixed. Something that I want to emphasize here is that this was just part of the story, because when you start ramping up the condition numbers of the problems that you're dealing with, this starts deteriorating as well. I mean, all methods start deteriorating, right? So all first order methods deteriorate. So to address this fact, we try to use preconditioning, right? So preconditioning would entail learning some kind of information about the Hessian that is behind these iterations, right? So, and then what we did was a series of works where we used a Bayesian setup. Essentially, we set the problem as an estimation of the Hessian matrix on the space of positive definite symmetric matrices, using as data the different increments that we are recording on the stochastic gradients and their averages. So based on that, one can postulate a Gaussian likelihood, and then of course with the prior that one has, knowing, for instance, not only just the positivity definition, definite of the matrix, but also maybe a bound on the spectrum of this Hessian, we can introduce all that, right, and produce effective preconditioners for the system. There's a price to pay. So per iteration, right, if you're working on a space of features that have a dimension d, then if you just use this, right, you will have to pay d cube for each iteration. So you get acceleration in terms of number of iterations and gradient evaluations, but each iteration is a bit costly. Then we moved into some sparse version of that, right? And that reduces the complexity of this d cube into d square. And finally, there was a limited memory stochastic BFGS that only cost OOV per iterate, and still, if you're lucky and your program actually has some kind of subspace that contains most of the information, this is a very good alternative. So how does it work in practice? Actually, now you see here something that has a condition number indication of the order of 10 to the 12, right? So you apply your favorite first order methods, they just do nothing, they stay like horizontal, right? But if you start applying this sort of preconditioning, you can still go ahead and get a rather okay convergence. This is a comparison between the things that we do. This not. I mean, this is the one of the ones that I mentioned in the previous slide, and then two competitors on the literature here. I think this is an advantage, and you can see already in the runtime and the epochs with respect to the convergence. And still, not only the kappa, the condition number is large, but also the dimension, right, is not a toy, right? We are on the order of 1,000 dimensions. All right, so then there was a line of research that actually covered many works in the group, and this is to use stochastic optimal control for important sampling. We are interested in evaluating rare events, for example, probabilities of failure, and as you know, when you try to use Monte Carlo methods, right, you will suffer because you will never hit essentially a certain threshold, right, unless you use a humongous amount of samples, right, which is prohibitive. So in some way, you want to introduce, in this case, for example, you have a dynamics. This may be an stochastic differential equation. You introduce a change of measure through the Girshanov theorem, and then you're able to tilt these things upward, and you have to introduce a Raúl molecular factor in the expectation to keep things unbiased, right? So if you choose the tilt in a correct way, right, you're able to reduce the relative variance, right, and get away with much fewer number of samples. All right, so how do we do this? Well, if you just do it in an ad hoc way, you may know certain characteristics of the problem, and then you're able to come up with a certain policy to tilt the paths. If you want to do this optimally, right, the way to do this is to say, okay, I'm going to consider my Girshanov transformation as a control, right, and I will try to minimize the second moment under the new measure, because the first moment is not changed, right? So if you want to minimize the variance, the only thing you have to do is to minimize the second moment. Okay, so now you can write Hamilton-Jacobi-Wellman equation, right? Because this is a Markovian process. You can write a Hamilton-Jacobi-Wellman equation and set up to solve it approximately, and this will provide an approximate policy to change automatically without knowing much about the system, right? Then the measure to adjust for optimal sampling. Of course, this has applications in many things. I'm writing here stochastic differential equations, but we also work in stochastic reaction networks, right? So it doesn't need to be this. We work also in Makin-Vlasov and other equations as well. I think I mentioned this already. And the key that is behind is how you actually solve the Hamilton-Jacobi-Wellman approximately, again, because you don't need to solve it in a super accurate way, so that it produces a policy that helps you to do this, right? So you can use some tricks of finite difference, finite elements, sparse approximation. You may know some ansatz that works well of this value function that is behind the Hamilton-Jacobi-Wellman equation, and then learn it because you parameterize it in this family, and then you learn the parameters through samples of these stochastic paths, right? In the process, of course, you have to be able to provide stochastic gradients, right? And that is not a triviality in certain situations. Sophia here working her PhD in that particularly for stochastic reaction networks, right, which are processes actually that live in a lattice. So you cannot talk about derivatives in the usual way that you talk with here on a neat stochastic differential equations, where you can actually apply derivatives here and get a variation of the path with respect to initial conditions and things like that. In the other case, you have to be way much more subtle because everything is discontinuous, right? But you can still do it. So that was a great work, by the way. Okay, so in relevant probability estimations, like I said, you can have these really big advantages through the importance sampling, and in high-dimensional stochastic reaction networks, for example, we have observed 500-fold variance reduction for 6-dimensional examples, and we have tried higher as well. But this was one piece of data that I could get. There's another thing, right? One of the things that appears challenging when you try to apply this, and I said tricks before, right? I said when you have to apply stochastic optimal control in this setup, you need to solve a Hamilton-Jacobi equation, and then you have to apply some tricks to be able to deal with the dimensionality. In principle, if you try to solve the Hamilton-Jacobi, you will have to solve it in the dimension of the underlying, right, which is in this case 6-dimensional plus time. That usually is not possible. Right? I mean, unless maybe you use sparse tensors or things like that, it's not directly available to you. So one way to deal with it is to do dimensional reduction using Markovian projection. Essentially, this is called mimicking in some I mean, depending on who you talk to. It's linked to Jonji and other people. And the idea is to produce an approximation of the high-dimensional system, which is in this case 6, for example, that could be maybe of 1 dimension that would still mimic or reproduce the marginal distributions of the observable that is the goal of your computation. Right? By doing that, you actually capture essentially the marginal distribution in a perfect way. And remember, when you look at an important sampling problem, right, you always try to compute an integral of a density or a probability mass function times a function, right? If that function is your observable, so if you actually look at what is the optimal transformation, you know that actually is proportional to the product of these two functions, right? I mean, right? It's probability mass function times the other. So if you're able to capture or to use a dimensional reduction that still captures the distribution of at the final time, that contains most of the information that you need to establish this stochastic optimal control. Okay, what's the key? The key is actually that this Markovian projection can be done, for example, onto 1 dimension that is connected to this observable, starting from 6 dimensions in an efficient way via regression, for instance. That's not an optimal control problem, just essentially an integral, right? So that's easy. Even if it is high dimension, you can have good answers for this projection. And what are you left with? Well, once you do that, you only have to do the Hamilton-Jacobi in 1D plus time. Sometimes, and I have not seen yet some things like that yet, for variance reduction, you may need 2 dimensions to capture the things. But so far, we have tried, and we never seen a problem that actually, of the things that I'm describing, that needs much more than 1 dimension to get a very serious variance reduction. Okay? So, solving the Hamilton-Jacobi in that setup, not a big problem. Okay, so you can also go to Makin-Blasov, right? And in Makin-Blasov, I work right at the beginning with Abdul Latif, right? In non-relevant setups. And there we were able to use, by using a math index Monte Carlo in the number of particles and the time steps, to bring the complexity essentially from 10 to the -5 to 10 to the -2 up to log factors. Just by doing the sampling in a clever way without changing the integration, which was essentially Euler-Maruyama for the particle system. Now, the challenge in this research was to actually mimic those results, but now within the realm of rare events. So how much do you have to pay in terms of complexity when you go from non-rare to rare events, right? And essentially, you can actually get the same things. We also work in chance-constrained optimal control in wireless networks via Lagrangian realization. I think there will be a poster by Sham, who has defended his thesis very recently, or Sham actually. Sham? Yeah, the little Sham. Okay. Again, one has to play with tricks to deal with these stochastic optimal control problems. I mean, what you're trying to actually satisfy a certain degree of quality in the delivery of your signals, right? Subject to some demand that is connected to the base that is actually satisfying the customers, right? And the quality of the channel for the delivery, right? That is changing as well, and so forth. So you would like to essentially ensure that with a certain probability, right, you are able to fulfill your service, right, while minimizing certain costs. Well, once you introduce a chance constraint, you lose the Markovianity. Okay, so you have to, if you want to again bring this back to a Markovian setup and be able to use Hamilton-Jacob-Bellman and other things, you have to introduce a relaxation. Okay, so that's what it is. We introduce a particular kind of relaxation that allows us to bring this back to a Markovian setup, and then we have a two-level iteration because we have to work to find out this dimension, these dimension values. Right. So moving from there, right? There was another line where we have to deal with nested expectations. These are sort of nasty coupled integrals that appear naturally in the computation of expected information gain in Bayesian optimal experimental design. And Arvid also defended, very recently his PhD, dealing with situations like this, where you have to integrate something that has a nonlinear function here of a conditional expectation, right? So you cannot just write down this as a single integral because of its nonlinearity. If this will be linear, you can do what you can in general. Not only that, this f has a singularity. Usually in this sort of the expected information gain, it will be connected to a log, right? But things can get nasty. And on top of that, if you want to go, for example, from Monte Carlo to quasi-Monte Carlo, you have to map things that actually are Gaussians into the hypercube. And then by doing that, you bring things that are in an unbounded domain to a bounded domain, you introduce singularities. That's unavoidable, okay? You have to be singular when you do that. And then you actually have to deal with those singularities, not just with the singularity at zero, right? And that required not just clever tricks, but also systematic error analysis for the understanding on which are the things that you can do. For example, a truncation of a certain kind in the unbounded noise to be able to still produce the results in complexity that you will have with a function without singularities, up to a log factor of the tolerance you want to achieve, a multiplicative log factor of the tolerance you want to achieve. So that's great, actually. We are pretty proud of that. And in this process, like I said, up to log factors, one was able to bring the complexity, for example, from this 2 to the -3 plus something that is connected to the solution of the PDEs that you have to solve for each of these samples. Because again, remember, this is an optimal experimental design. There's a model for the data. The model for the data is usually connected to a finite element or some other discrete PDE method that is predicting what the data will give for a given set of parameters, right? So that you must have essentially, right? And then there is this reduction from 3 to 1 by using these methods that I was referring to. Essentially, they're hierarchical, right? In nature, so you introduce multi-level, right? And again, you have to work to couple things correctly. There are a lot of subtleties here. For instance, in the usual multi-level, for instance, you will have randomizations in all levels right here, because you have these two integrals. It turned out to be very beneficial to shut down the randomization of one of the integrals at one of the, at the lower levels, right? To be able to reduce the variance and achieve the optimal complexity. That's technical, but you can talk to Arvid, right? And he will explain you all about it. It's a lot of fun, but very hard work. not just at the analysis, but also the development of the work, because that particular trick was crucial to get the best complexity. We also work in efficient Fourier pricing for computational findings. In computational findings, as you know, you can use the simulations based on paths, right? But whenever you have more structure, you can use it to get better results, right? So what's the usual thing? If you're just pricing European options, say, you have to compute the expected value of a payoff times a density or a probability mass function, depending on your model, right? And you have to integrate this. What can go wrong? Well, if you try to use a quadrature, two things will happen. One is that you may be in a dimension that is high, so you have to try to apply some sparsity to deal with it. But the other thing that is actually a bad combination with the fact that you're in high dimensions is that you can have non-smoothness. Okay, so non-smoothness connected to high dimensionality, that's a bad mix. And then what can one do? Well, if one has, like I said, structure, and by structure here we mean that we know something about the Fourier transforms of these functions, then we can use again Plancherel to move this into the Fourier space. And what will we gain? Well, actually, if you have some non-smoothness in the normal space, in the Fourier space, you may be able to smooth it out, right? And you may get oscillations, but at least not discontinuities. In that case, when you know these things explicitly, then and you could do this semi-analytically too, because you may have some way to write these functions in terms of the solution of some deterministic order differential equations and so forth, right? So you can write this and be able to evaluate in an efficient way. So now you're left with an integration in the Fourier space of something that has high regularity that the original thing you set up with. Well, things are not over yet, right? If you try to apply blindly sparse methods, you will fail very likely. Okay, why so? Because, well, you have to use what is called damping techniques to be able to control the growth of these functions, right, in a particular way. And to find this damping is not obvious. The literature didn't explain this clearly, right? So to develop that, the damping was part of the research, and it worked quite well. And once you develop this damping, the resulting integrand has a better behavior. You can use, for example, adaptive sparse grid quadratures, understanding the analyticity properties of the resulting function, right? Like one did, for example, long ago with Fabio and others in the context of linear elliptic equations with randomness in the coefficients, right? Here, it appears naturally in this context of trying to understand what would be the best way to apply sparse grid quadrature for the optimal damping. You can also apply quasi-Monte Carlo as well. That seems to alleviate the curse of dimensionality quite a lot. As we will see here, right? You see here the dimension ranging up to 15, right? Which is not negligible in this case, right? Where you compare some of the cost of a certain just tensor product, right? That is just madness, right? In this setup with randomized quasi-Monte Carlo, right? And Monte Carlo still not being able to beat this randomized quasi-Monte Carlo that use the optimal damping. So more of this, you just talk to Michael, who will be able to talk not just about this, but many other things that we have been doing in this area of Fourier. And I don't have the time, for example, to talk about stochastic and rough volatility. There's something that is being done. 5 minutes? Wow. Okay. I've been very, very lush with my time. Okay, so other things, and I'm going to accelerate now because I have to get to the end. Computational machine learning was another thing of the things that we have been doing. The idea here is to approximate a function, right? And to approximate this function, you can say, okay, I can use a Fourier transform and discrete Fourier transform and try to find out which are the optimal frequencies to retain to approximate the same. Well, in principle, the optimal frequencies are not given to you, right? And that's sort of a base approximation problem that is very difficult to solve. So one way to go around is to try to create a random walk, right? Or in the space of features, in the space of frequencies, sorry, that we try to capture the best frequencies for this thing, and then given the frequencies, you can find the amplitudes in an easy way, just solving least squares. Okay, so first there was a Markov chain-like type of walk to do this, and lately Eric actually came up with an idea, and we all followed through. Eric is there. Okay, you can say hello, Eric. You're very shy, but okay, I push you to do this. So a resampling idea appeared that it was inspired in particle filters essentially, and this was a huge boost in the convergence of these sort of walks, and then one could get much better results. For instance, here, just as a topic, right? Because I mean, numerical analysis, we're always boring, right? So we solve a problem. We're very excited, and what do we show? And I'm very proud of that, by the way. We show the error going in a certain rate, right? Or the work versus the tolerance going at a certain rate, and we beat other methods. Fantastic. We're all happy. Normal people look at that and say, oh, okay, underwhelming, but it's great. Now, in this case, we can show a picture which maybe even non-numerical analysts will appreciate. So here you have what is called an interpolation of on a given picture, which is called immaturgation. Essentially, you're trying to guess points in between a certain image, and this is the method that I was talking about with resampling, right? And these are methods that actually try to guess in an ad hoc way the content of the frequencies, right? And then produce super bad blurring, right? And there's much more to it, of course. And you can talk to Aku and to Anamika as well, not just to Eric, that are over there. Aku and Anamika, you can raise your hands. Okay, good. I don't have the time to discuss spectral bias, but you can talk to them as well. I'm running out of time. Yang Liu, that is over there, right? And Yang, you can just say hello. Finished his PhD also recently at KAUST, and has worked with quasi-Monte Carlo and Monte Carlo for linear elliptic equations with the coefficients that are log normal, right? These are challenging problems because the log normal, as you know, is not a uniformly bounded coefficient. So in principle, you don't have uniform coercivity, not continuity in this problem. You have to be careful, and you have to, at the same time, we followed up on the work from 2006 by Cepesi and collaborators on optimal mesh refinements, right? And then we extended it to this case of random. That was for the deterministic problems, and we extended it for this case of log normals, right? So if you want to remember something, remember this table, right? This was some finite element, and the adaptive material Monte Carlo in this case can improve from the standard material Monte Carlo, usually uniform meshes. Of course, it's not resolving the similarity, but in terms of the strong error is rather competitive, and strong error is actually what mostly defines the convergence of the multi-level. But as you start going up in the dimension, same discretization will yield, even you see here, dimension 4, right? A square root of complexity with respect to what we can do with adaptive methods. Okay, so I already mentioned the teaching and training legacy on the master level and the bachelor. I also forgot to mention that we established a pipeline from Tunisia, from the École Polytechnique Tunisia, and we also ran as a node on the Erasmus exchange program that was very successful. We have a vast network of collaborators. This is not the same map as I showed you before, right? I mean, so this is another map of the collaborators, and again, it's not complete. I didn't put it up today. So we raised the profile of UQ in RWTH through the years. We established collaborations in KAUST, TFL, and other big networks of research at RWTH and even UNISH, in the GSE. And here we have Wolfgang. Wolfgang served as the main head of the GSE through the years, and we are thankful for the support of the network to pipe some of our students through those. We also discussed a little bit the success of the alumni. And what about the future? Well, the future has many things, and again, I cannot mention everything we do because then I have to kill you. No, I'm just having fun. these are some lines that we do, and for the sake of time, I cannot mention everything. We will still continue with hierarchical importance sampling for relevant computations. AF, for example, that is over there, can mention a little bit about the combination of importance sampling with multi-level methods, right? We will continue with the complex stochastic differential equations and how to compute efficiency in those. We are moving through stochastic optimal control with incomplete information, chance constrained stochastic optimal control, as I mentioned, and the stochastic optimal control for non-Markovian processes as well. Continue with the computational scientific machine learning. Energy is one of the main examples that I'm interested in, so we're going to keep working on those, right? And we will still rely very much on the strength of our teams and the extended teams, so our network of collaborators. For example, Fabio, who's has been a big supporter, and Christian over there, right, that are pillars in our development. So and with you guys, we can do much more, and without you, very little, in fact. So thank you so much. Let's see if I managed to reach the time.